So this next example needs a little bit of thought. The first thing to recognize is that we've got some sort of four-stroke cycle going on. And so we've got some information here. A four-stroke cycle, this was news to me, is completed during 2 full revolutions of the crank of the flywheel. So the working stroke during this 4-stroke part will be half of 1 complete revolution. So the 4 strokes is a half a revolution, then the other half, and then a half of the second revolution, and then the final half. So that's where the 4 strokes comes in. So the working stroke corresponds to half a revolution, which is 180 degrees, or pi radians. So that information would be given to you in a situation. So you do need to understand that before you can go much further with this problem. So what's happening here is we've got a flywheel that's already rotating, and then we're going to do some work to it, which is going to mean that it's rotating now more quickly. So it's got more kinetic energy. So what we need to find out is the final speed of the flywheel once this half cycle, this working stroke, has been applied to it. So we have a situation where we've got a flywheel and its velocity at the commencement of the working stroke is 240 revolutions per minute. That's not the velocity, it's the frequency, but we often talk about velocity in terms of frequency. I've no idea why, it's just very confusing to me. But as soon as I see something like revolutions per minute, well, I know that means frequency. So it's got that frequency. And then we're going to apply this working stroke to it. So we can, if that's the frequency it's rotating with now, then it's going to increase its speed, and we want to find out what that final speed is. That's the sort of idea of the problem. So we're going to find out the kinetic energy that it's got at the commencement of the cycle, and then we're going to find out how much extra energy we're giving to it by calculating the work done. And then we're going to add that kinetic energy onto the initial kinetic energy to find the final kinetic energy. And then from that we can find the speed. So the process is found by A, calculate the initial kinetic energy at the start of this working stroke. Calculate the work done during the working stroke. And so then we're going to say that the final kinetic energy after the working stroke equals the initial kinetic energy plus this work, ignoring energy losses again due to friction. And then once we've got that in final kinetic energy, we can find the velocity. Which is the overall aim of the problem, to find the final velocity of the flywheel. So if you care to pause, if you're watching this video and you care to pause it at this point and have a go, those are the steps A, B, C and D. So what I'm going to do now is pause it and ask you, we'll work through these. So part A, calculate the initial kinetic energy of the object. So have a go at that and then we'll look at it together. As before, as usual, extract the information. What do we know? What unit, what symbol do we give those things that we know? Are they in appropriate units? And so on. So first job, extract the information. So that's the information. We know the torque, we know the mass, we know the radius of gyration, and we know the frequency, which we need to convert to hertz. So now let's go through the problems. Part A, find the kinetic energy at the commencement of the stroke. So you could set it out a bit like that if you wanted. Do it in one hit. Kinetic energy is a half I omega squared. I is mk squared, so I could put that in there like that, times omega, which is 2 pi f, the frequency is 4.3, all squared, so I need to put that in a bracket. So the red bracket is unnecessary, but we can put it all into the calculator and we get the kinetic energy to be. That gives us about 63,871 joules. Leave it in joules because we're going to use this value late in the calculation rather than convert to kilojoules. So now for part B, we need to calculate the work done in our process. Calculate the work done during this working cycle. So what's the formula for the work done? The work done in a rotational example is the torque, the force, times the distance moved. The torque we're given, but the distance moved, of course, is the distance during this working cycle, which we've already said was pi radians. So the distance travelled is pi, so the work done is just the torque, which is 1060, was it? Yeah, 1060 pi. Leave it in terms of pi. Is appropriate at this stage because we don't need to know the work particularly. If you're asked what the work is, well then you might work out an answer around it. So that's the work done. Now the science, the engineering comes in a way. We've worked out what the kinetic energy was before the working cycle, 63,871. We've now done 1060 pi joules of work, so the final kinetic energy, ignoring energy losses, hopefully, common sense would tell us we just add them together. So the total kinetic energy, the final kinetic energy, is the initial kinetic energy plus the work. So that's what I'm going to do. So that equals 63871, or whatever value you use, plus 1060 pi. (67,201 joules). So that's part C. We've calculated now the final kinetic energy. So now we want to find the angular velocity. So now we use the formula for angular velocity. Square root of twice the kinetic energy divided by the mass. But in this case, that's going to be I, the moment of inertia, isn't it? And we know the moment of inertia. We calculated that earlier, so we can put that in. Or, actually, twice the kinetic energy divided by mk squared. So we can now literally put the numbers in. 2 times 67,201 over, because the calculator allows us to do this, mass, which was 500, I think, was it? 700 times the radius of gyration, which is 0.5 squared. So I could put it into the calculator literally just like that, and it will give me the angular velocity. Use the calculator, use the the operations on the calculator to help you get a more accurate answer rather than doing it in stages, if you're feeling confident. So 27.92, now this value might vary, but of course once we round it, and if we look back to the original question and the information we were given and look at the accuracy that we're given here, 3 significant figures, 1 significant figure, 1 significant figure, 2 significant figures. You go by the accuracy of the least accurate number you're given, so 1, maybe 2 at a push. So I'd probably round this to at most 2 significant figures. So if I rounded that to 2 significant figures, I'd call it 28 radians per second, and I wouldn't mind betting that whatever values you use, if you round it to 2 significant figures, we're all going to get the same answer. So that's where the accuracy sort of comes in again. So about 28 radians per second will be the final angular velocity. Okay, so let's just have a look back at this again. Now, the difficulty is not in putting the numbers into the equations. That's the easy bit. The difficult bit is sussing out which equations we need to use from the information given. And this is a bit of an awkward example because of this. You know, you need to understand that the working cycle is only 1/2 of 1 revolution. And you need to understand that the work we do adds to that kinetic energy of initially, and so on. So it's understanding what's involved. In other words, it's getting to this bit. That's the awkward bit. Sussing out what we've got to do and in what order to solve the problem. Once you've done that, and you've extracted the information and got it in the appropriate units, the rest, with practice, is plain sailing. I hope you'll find. Okay? Okay.